Let's take another example. I have three reactions here, and we're going to use those three reactions to find the change in enthalpy for a fourth one. So we've got methane reacting with oxygen to give us water and carbon dioxide, and we have a change in enthalpy of minus 802 kilojoules per mole. We have a second reaction, 2 moles of water decomposing to 2 moles of hydrogen, 1 mole of oxygen, and that has a change in enthalpy of plus 483.8 kilojoules per mole. And a third reaction, we have carbon dioxide decomposing into carbon and oxygen, and that has a change in enthalpy of plus 393.4 kilojoules per mole. We're asked to find the change in enthalpy for methane decomposing into our carbon and our hydrogen. And this is a reaction that typically doesn't occur, so it's very difficult to measure that change in enthalpy. But what we can do is add these reactions. So in our first reaction, we've got our components, we've got our methane, which is what we require. We add oxygen to that and we burn it. It's a combustion reaction, and that will give out 802 kilojoules per mole. So we get an exothermic reaction. We can then take our water component in our second reaction, decompose it into hydrogen and oxygen. That one will be an endothermic process, so that's why we're moving up slightly. We then take our third reaction, which is to decompose our carbon dioxide into carbon and oxygen, to give us our final products, which will be our carbon and our hydrogen here, and our oxygen is being recycled because we've got our oxygen in this system as well. So effectively these three reactions are exactly the same as our reaction our reaction from our starting point to our end point of this particular reaction. Now, if that's the case, then the change in enthalpy for this particular reaction should equal that one plus that one plus that one. So if we add those values together, we get a value of plus 74.8 kilojoules per mole. And that represents the change in enthalpy when we decompose methane into carbon and hydrogen. The previous example was reasonably straightforward because we didn't have to manipulate the equations. However, this example we need to do something a little bit more complex. So we've got three reactions again, three standard reactions. We've got iron oxide plus carbon will give us iron plus carbon dioxide, and that has a change in enthalpy of minus 272 kilojoules per mole. We've got a second reaction, iron 3 oxide reacting with carbon to give us 2 lots of iron plus 3 lots of carbon dioxide, and that has a change in enthalpy of minus 824 kilojoules per mole. And then a third reaction, carbon reacting with half a mole of oxygen to give us carbon monoxide, and that has a change in enthalpy of minus 111 kilojoules per mole. We're asked to find the change in enthalpy for a reaction of iron oxide to iron 2 oxide plus half a mole of oxygen to give us iron 3 oxide in its solid form. Now, if we look at this particular reaction and relate it back to our previous ones, we find that our iron oxide needs to be on the left-hand side, which it is. So we need 2 moles here and we've only got 1 mole. That means we need to multiply reaction number 1 2 times. So we get 2 moles, 2 moles, 2 moles, and 2 moles. This also means we need to multiply our change in enthalpy by 2 as well. So 272 by 2 is minus 544 kilojoules per mole. Now, if we look at our second reaction, our reactants and products are on the wrong side for our reaction that we want to find. So we see that we've got the iron 3 oxide on the right-hand side here, but it's on the left-hand side here. That means we need to reverse this reaction. So minus 1 times reaction number 2 will give us 2 lots of iron plus 3 lots of carbon dioxide, gives us the 1 lot of iron 3 oxide and 3 lots of carbon. We've switched this around. If we switch the reaction, we also need to switch the change in enthalpy. So we've gone from minus 824 to plus 824 kilojoules per mole. Our reaction number 3 we have everything on the correct side and in the correct ratios. So we can use that particular reaction as we need it. Now, according to what we said in the previous examples, if we add these three reactions together, that should give us the reaction that we require. So let's test that. On the left-hand side, we have 3 lots of carbon, and on the right-hand side, we have 3 lots of carbon. On the left-hand side, we have 2 lots of iron, right-hand side, 2 lots of iron. On the right-hand side, we have 2 lots of carbon monoxide, 3 lots of carbon monoxide, which cancels out with our 3 lots on the left-hand side. So we're left with a reaction, 2 moles of iron oxide, iron 2 oxide, plus half a mole of oxygen, gives us 1 mole of iron 3 oxide. And that's the reaction that we need. So we've now balanced that reaction. We can now look at calculating our change in enthalpy. And for that, we need to add reaction number 4 to number 5 and number 3. And if we calculate that value, we come out with a number of plus, so it's an endothermic reaction, 169 kilojoules per mole. So the change in enthalpy for this particular reaction is plus 169 kilojoules per mole. So if we summarise the steps that we went through, this will help us in calculating any Hess's law question. First of all, we need to rearrange each equation so the reactants and the products are on the correct side and with the correct number of moles. And we went through that in this particular example. We then need to change the sign and adjust the change in enthalpy by the same multiple as we did in the first step. So for reaction number 1, we had to double it because we doubled the number of moles through here. For reaction number 2, we needed to reverse the sign. So we've got to ensure that we do that. Our third step says that we add all the equations together, and this will ensure that we have the correct equation for the one that we need to find. And then finally, as we did here, we add the change in enthalpies to give the final change in enthalpy value for the reaction that we require.